we have seen two important questions. The one was explain the construction and operation of JFET with need diagram, and the other was a small signal model of JFET. Now today we'll be covering frequency limitation, right? So in this frequency limitation, this if it will be asked, it will be asked for 4 or 6 marks. Okay. So here what is main important thing is you have to redraw the small signal equivalent circuit of JFET with capacitance, right? So why we have to consider the capacitance? Because we are looking into the frequency, right? So when frequency term comes, the capacitor plays a very important role. Why? Because whenever we speak of any frequency, that means it is AC signal, correct? Because DC signal has zero frequency, but AC signal has some finite frequency. So whenever we speak of AC signal, that capacitor comes into picture because capacitor is responsible for passing that AC, whereas it blocks the DC. Okay, so we are considering the capacitor here because we are considering the AC. And why we are considering the AC signal? Because we are talking about this frequency, right? So what do you mean by frequency limitation? What frequencies, what is the maximum frequency that can be applied to the JFET, right? Say I am applying a sinusoidal signal, a sine wave, right? How much maximum frequency it can have so that JFET will respond to it. It will function correctly, right? Can I apply infinite frequency? No, it is not possible. Every device has its own limitation, right? So we are speaking about what is the limitation of frequency when we say about JFET, correct? So here you need to remember two things. What two things are coming here extra? The two capacitors, right? CGS and CGD, only two capacitors. So here whenever we speak about frequency limitation, right, there are two things which affects the frequency limitation. The first thing is channel transit time. Channel transit time. What do you mean by channel transit time? The time taken by the charge carriers for transition. Channel transit time is the time taken by the charge carriers for the transition in the channel. What do you mean by transition? For the movement, right? So the charge carriers require some ample amount of time to move from one point to the other point, say from source to drain. Electrons moves from source to drain in JFET, so it requires some time, right? That time will be considered for frequency limitation. Why? Because actually frequency is directly or frequency is inversely related to time. What I was trying to say, frequency, whenever the term frequency comes, time will definitely come there, and that time itself is responsible for limiting that frequency, because if the time is more and more, the frequency will be less and less. If the time is less, the frequency will be more, right? So that channel transition time, it is responsible for frequency limitation. How? If the charge carriers require more amount of time to transit from one point to the other point, that is from source to drain, then the frequency will be lesser and lesser. That means the JFET will respond very slowly, right? It cannot take a very signal of very high frequency. It cannot take, correct? The second point which affects the frequency limitation, what is that? Capacitance charging time, right? So here we have capacitors, correct? So in network theory you might have studied some time is required for the capacitor to charge up, correct? So that charging time of this capacitor, that also limits the frequency, right? So in the previous video I have explained clearly by drawing the sine wave and charging and discharging time of the capacitor. So this capacitor, if it's charging quickly, then it is very good. so that frequency can be higher and higher, right? So the two factors which affects the frequency limitation are, you have to underline these 2 points: the channel transition time, the channel transit time, and the second one is capacitance charging time, right? And then we have the maximum frequency derivation, right? So you can remember simply the final formula. The maximum cutoff frequency can be written as Ft equals to E into mu n nd a square divided by 2 pi epsilon s L square, right? And depending on that, we may have one problem also in the exam. So this was about frequency limitation, right? Then I think, yeah, we are into the MOSFETs now. MOSFET is another type of transistor. Right. So here, how the MOSFET is manufactured or how the MOSFET is fabricated, those steps are given. So what is MOSFET? Metal oxide semiconductor field effect transistor. Metal oxide semiconductor. Upper layer is metal layer. Middle we have oxide, and below we have semiconductor. Correct. So metal oxide semiconductor field effect transistor. What are the fabrication steps? Fabrication steps are as follows. You have to draw these diagrams, correct? So first point will be, again, basically it is with the pure semiconductor, but here they are showing with the p-type semiconductor. That is p-type silicon, right? So first step is pure semiconductor. Dope it with the p-type material, it will become p-type semiconductor. Then you have to apply the silicon dioxide, then photoresist, correct? I'm telling you stepwise. After photoresist, use the mask for etching, correct? So after using the mask and applying the UV rays, you can etch the unwanted part by using the chemical reactions, correct? So this is done by etching. So here it is written etching of SiO2, correct? Then you have to ion implant. Why did you etch? Because you wanted something there, right? So that something can be achieved by ion implantation or doping of N plus, correct? I'm going a little faster because these things are very easy. After that, again you want something, correct? For that, again you will develop photoresist, then use the mask, apply the UV radiations, and then again etch. What we require now, we require the gate, correct? So for formation of gate, we have etched it. Sorry. So after that, again what we do, we just do with the metallization. That is, aluminum is applied over it, correct? And then take out the terminal from the metal, correct? So this is source, gate, and drain. So unwanted aluminum, see, aluminum was applied throughout the substrate, right? But unwanted aluminum can be again etched away. So here we are etching away the aluminum, right? So these are the fabrication steps for MOSFET, right? Next is energy band diagrams of the JFETs. Right? So everywhere in the syllabus, what you are seeing lot many diagrams, right? So very basic, fundamental thing required in the exam is you have to draw the diagrams very neatly with the proper labeling, correct? For that, try to practice. Don't don't miss anything from the diagrams. Okay. I had said you yesterday also, if you miss one or two sentences in the explanation, no issues, right? It is manageable. But if you miss the diagrams only, then you will straight away lose 50 to 60% of the marks, right? Only theory will not fetch you marks. Only diagrams will not fetch you marks. So here energy band diagrams of JFET. So here what we are doing, we are just considering the conduction band, valence band, Fermi energy level, right? So how is this? Applying positive towards the gate. correct? So positive towards the gate means the electric field will be from positive to negative, right? So at this time, how your accumulation of holes will be happening? Yes, the Fermi energy level will be near to the valence band, right? So how this diagram can be interpreted here? This is vertically, right? So upper layer we have gate, below that we have SiO2, that is oxide, below that we have substrate, correct? So it is rotated 90 degrees. This gate has come to the left hand side, it was top, correct? Then intermediate was oxide, here we have the oxide. Below that was the substrate, here we have the substrate, correct? So in the substrate, what is happening, right? So that thing is being represented with the help of energy band diagram. So Fermi energy, it is near to the valence band. Correct. Why it is near to the valence band? Why? Because there is accumulation of holes. Correct. See, that energy band diagram, it is related to this diagram. Here I am giving negative supply. Correct. Negative supply means what? Here towards the gate, all negative charges will come. In between we have oxide, below we have substrate, correct? So because there are negative charges on the gate, in the substrate there will be positive charges. What do you mean by positive charges? Holes, correct? So holes will be accumulated near the p-type substrate, near the oxide. Are you following?
Yes.
So when I apply negative potential at the gate, holes will be accumulated in the substrate, that is represented in this diagram. Negative potential at the gate, holes will be attracted towards the oxide and substrate interface boundary of this, correct? So when holes are there, holes will be always in valence band, electrons will always be in the conduction band, correct? So holes are the majority carriers here, hence the Fermi energy level EF, this dashed line, it is near to the valence band, correct? Because there are holes, correct? If I apply positive voltage, what will happen? If I apply positive voltage, what will happen? Here it should be negative. See, here it is positive, means here it should be negative, correct? When negative means what? Electrons, correct? So when we say of electrons, right? Electrons will be accumulated on this surface, correct? Electrons will be accumulated on this surface. So when I apply positive, electrons will be accumulated on the surface, correct? And now you can see where is the Fermi energy level, it is being shifted towards the electrons. See, this is bending, correct? This is bending. Why there is bending? Because of large positive voltage. If you go on increasing the voltage, it will bend more and more, correct? And here you are seeing the electrons are being accumulated, and these accumulation of electrons are near to the Fermi energy level, correct? So this valence band has bent in such a way that it has moved far away from the Fermi energy level, and this conduction band, it has come near to this Fermi energy level. Fermi energy level will not bend, never it will bend, right? So these diagrams you have to explain, and you have to draw and explain. How to explain? Take different cases. What is the first case? First case is apply negative voltage at the gate. So what happens? Positive holes will be attracted near the substrate and oxide boundary, correct? So because of that, what will happen, that you have to explain here, right? So holes will be attracted as shown in this diagram also, and Fermi energy level, it is very near to the valence band and very far away from the conduction band, correct? How is the electric field? Positive to negative. Where is positive? Here is positive, here is negative. So in this direction it will be there. With pencil it is marked. Following? Are you following? Are you following?
Yes, sir.
Second case.
Yes, sir.
Second case you have to take. So this is first case, right? Second case you have to take. Second case is applying positive voltage here. Correct. So when you apply positive voltage here, negative charges will be developed in the substrate, right? Or you can say between the boundary near the boundary between oxide and substrate. So this is the diagram for second case, correct? And if you go on increasing this voltage, more and more electrons will be attracted and the band will bend more and more, correct? So that thing you have to explain it in your own words, no issues. You can use your own words. But please remember, diagram should be very, very neat, correct? Now inversion has happened here. Earlier there was accumulation, now it is inversion. And these are again the diagram for the opposite case, correct? Opposite case means here we had p-type substrate. Here we are choosing n-type substrate. So bending will be just reversed. Nothing, no change, correct? So here you are able to see accumulation, then comes depletion, then comes inversion, correct? So this diagram, what it is telling, some Q charge is developed here, correct? And when we change the voltage, there will be change in the charge dq. That dq is represented by change in the charge, correct? Q is the charge developed with the positive potential. dq is the charge change in the charge, correct? And what happens inside also there will be change in the charge, that is dq minus. Here it is dq plus, I guess. Here it is dq minus, or yeah, I think dq dash, correct? So this is for inversion mode, right? So as the potential at the gate changes, there will be corresponding change in the charge level on the other side, correct? And what this diagram is telling, the steps. The first step is accumulation, correct? The very first thing which we had seen, negative potential, correct? Then as we go on increasing, as we see, negative potential means what? This is zero axis, right? This is zero. Left hand side there will be negative potential. For negative potential there will be accumulation. As we move towards positive potential, you will go towards the depletion followed by the inversion, correct? So the more details you have to refer the video, because if I start explaining each and everything in detail, then I'll be stuck up with only one topic, right? So this question is very, very important. I had given two important questions yesterday, correct? The JFET construction and working, and here then small signal model of JFET, correct? Then third very important question is this one, energy band diagrams in the JFET, correct? So there are huge number of diagrams here. You have to explain two sentences for each diagram. What is happening in which case and all, right? What is happening in which case and all, right? And one more important question is about MOSFET. Construction of MOSFET and working of MOSFET. That will That will be there in the next slides. I think this one is done, right? Yeah, then this comes the MOSFET working, right? So here we will be having the MOSFET. So what is MOSFET? How it is manufactured? How it is the fabrication steps for the MOSFET? They are different. You have to understand the question. What are the fabrication steps for the MOSFET? They are these steps, right? Fabrication of the MOSFET. Whenever fabrication comes, there will be all these steps: oxidizing, photolithography, that is photoresist, masking, etching. All these steps comes under the heading fabrication, right? Whenever fabrication is not asked, only construction and working is asked, then you have to go with this answer, right? Both are very important questions. Especially this question is very, very important, where we have the working of MOSFET, right? How the MOSFET works. So these diagrams you can draw, right? Starting from here. How it is constructed? MOSFET is constructed how? Again, take the pure semiconductor, dope it with the p-type material. Two ends you dope it with the n-type material, correct? In the center you apply oxide, and above that you just metallize and call it as gate. Three terminals will be there: source, drain, and gate. Four terminal is substrate or body, right? Steps I'll repeat again. Take the pure semiconductor. Second step, dope it with the p-type material, correct? Again, in MOSFET also you have two types. Basically, you have two types. One is enhancement, one is depletion, correct? In depletion mode, the channel will be present. The channel will be present. So this is depletion mode. Here you are seeing there is some path between the two source and drain, right? But here there is no path, correct? So in depletion and enhancement, only one change. Channel will be already there. Channel will not be there. In enhancement, you should not say that channel is existing, right? You have to start with, take the pure semiconductor. Second step, dope it with the p-type material. Third step, dope it with the n-type material at the two ends, correct? Then fourth step, apply the silicon dioxide, right? And after that, apply the metal and give out the connections, source, drain, and gate. In depletion type, you have to include one more step or one more thing. That channel is also there. That is also achieved by the doping. Channel exists between source and drain, correct? How about the working? So for working, let me take the enhancement mode, right? So very first thing is creation of channel, right? The channel should be created before we start with the working, because there is no path. So for that path creation, we have to apply the potential. That potential VGS should be greater than the threshold voltage. If VGS is greater than the threshold voltage, then what will happen? Then what will happen? Electrons will be attracted, right? The positive potential, if we apply, electrons will be attracted. What if we apply negative potential? What if we apply negative potential? If you apply negative potential at the gate, here all positive will be attracted, correct? And when positive will be attracted, there is no use, because here we have n type, here we have p type. Because of positive, again we have n type, so there is no path, there is no correlation. Are you following?
Yes.
Others, are you following?
Yes, sir.
Yes, sir.
So the construction I have said, right? Now I am going with the working. In the working, you take two cases. First case, you take VGS less than VT. When you take VGS less than VT, you can say that when VGS is negative, that time what will happen? Positive charges will be attracted here and which will not help in conduction. You go with the next point, you increase this VGS, make it positive, and you just cross the VGS with respect to VT. That is VGS greater than VT. So threshold voltage is VT. Above that, if you give the potential at the gate, all the electrons will be attracted near the surface, and those electrons will form the N channel. Correct? This is nothing but enhancement mode. Channel is formed now. After you have formed the channel, then you give positive potential at the drain, that is called as plus VDS. And when you give the positive potential at the drain, electrons start moving from source to drain because the channel has been formed just now. Right? The electrons will move from source to drain. Correct? And when we say it is the electrons are moving from source to drain, then we can say that the current has started. Correct? Current has started. But here in the graph you are seeing different levels of current. VGS2 is greater than VGS1. Correct? VGS1 is greater than VT. So as you cross the VT, there will be some current. If you go on increasing that voltage, right, voltage at the gate, what will happen? If you apply more positive potential at the gate, the channel will become more and more stronger. Why? Because this more positive potential will attract more number of electrons. Getting? Understanding?
Yes, sir.
So as you increase the positive potential at the gate, the current level will go on increasing, right? And that in detail it is given here. Correct? So and now you go on increasing the VDS. You start increasing the VDS, the current flow will increase. Correct? It will increase, and but what is there? Depletion region will be there. This is P type, this is N type. Between these two, depletion region will be there. Correct? So what the depletion region, how it will be positive given to the N type, right? Reverse bias. So depletion region will be more here, and it will be less here. The shaded part you can see, right? And when we go on increasing the VDS, then what will happen? Then what will happen? You can see here, right? Channel will become thinner and thinner. Channel will become thinner and thinner. Depletion region will go on increasing and increasing. Correct. And because of that, again pinch off will happen. Just like we have seen it in the JFET. Pinch off will happen. Right. After pinch off has happened, the current will saturate. It will not move ahead. So these diagrams are very, very important. Try to analyze these, right? And if there is any doubt, you please get back to me in the coming classes. If you are not understanding, please tell me. I will explain it again. Right? Please refer to the videos which I have uploaded in the YouTube, right? With respect to these subjects, these topics. So this is 100% guaranteed question. Which one? This question. How the question may be asked? Question may be asked in this way. Explain current voltage relationships, right, with the help of working of the MOSFET. Or they can ask you explain the construction and working of the MOSFET with knee diagram. Or they may ask you explain the construction and operation of the MOSFET with the current voltage relationship, right? So there are different ways of asking the question. So these diagrams, along with these diagrams, right? If you draw and explain properly, definitely you will score better, right? So this is again taken from another textbook, right? So here you are able to see the depletion region. The gray shaded region is depletion region. The blue shaded region, it is the channel. Channel is going on decreasing here. Why? Because more and more positive potential is applied at the drain, correct? Because of reverse bias. So here I'll stop for today's class. Module 5 I'll take up in the next class. Okay. Please go through these. I repeat the important questions. Very, very important questions. Construction and operation of JFET. Construction and operation of MOSFET. Small signal equivalent model. Right. Then you will have one more question. You may have this question also, but the probability is not that more. Which one? Fabrication of MOSFET. Right. Still, you can just remember these diagrams, and if you remember these diagrams, definitely you can explain them because they are very, very easy steps, right? And this question is very, very important. Energy band diagram of JFET. Energy band diagram of JFET. JFET small signal model. JFET operation and work, operation and construction. Then come to MOSFET construction and working. MOSFET operation and construction. Right. So 4 questions. These are definite questions in the final exam. Is it okay?
Yes.
Yes, sir.